Okay, part 2 of improper integrals. So we covered improper integrals that have infinity or negative infinity in the limits of integration, like I'd see infinity or negative infinity here or here. There's another type of integral that we call improper, and it's not as easy to recognize. It's easy to see if I have a negative infinity or infinity in the limits of integration. I see the symbol infinity right there. But here's another possible reason we would call it improper. If the function is continuous from a to b except for one value of x, then we're not going to be able to use the fundamental theorem of calculus directly to evaluate this. So what do? There's a few possible cases. It depends on where this discontinuity is, because there's one value of x where this function is not continuous. It could be the left endpoint a, and in that case, what I do is I take the limit, or I'm doing the integral from a to b of f of x, and what do? And this is part of the running theme. Wherever the issue is, in this case the issue is at a, I replace a with t, and I do the limit as t goes to that. Now, there's a little technicality here. In a lot of cases this doesn't matter, but if it does matter, this is technically a limit as t goes to a from the right. That's because we want to stay inside the interval. So if I did the limit as t goes to a from the left, that would mean that I'm considering values of t that are a little bit smaller than a, which would not be in this interval. So I do the limit as t goes to a, but it's like for values of t that are in this interval. And like I said, in a lot of cases, you would get the same answer whether you did the limit from the right or the left or whatever. But if it matters, it is a limit from the right. Okay, so that's this case. The next one is similar. If the discontinuity is at your right endpoint, b, then, well, I do the integral from a to t, because I'm replacing the issue, which is b, with t. And I do the limit as t goes to b from the left, and that's for the same reason. I want to consider values of t that are inside this interval, and so I consider values that are a little bit smaller than b. So t goes to b from the left. And so that's what I do. So we covered the case where the discontinuity is at the left endpoint a. We covered the case where it's at the right endpoint b. It could also be somewhere in the middle. If it's discontinuous at some other value c that's strictly in between a and b, then I just break this integral up into two. I take this integral from a to b, and I break it into, well, there's the part that goes from a and then stops at c, and then there's another part that picks up at c and goes all the way to b. And of course, these two are going to be improper integrals. This one has a discontinuity at the upper end, so this is like this type. So I would evaluate this one this way. This one has a discontinuity at the lower end, so that's this type. So I would evaluate this one this way. But as long as we know how to do that, we can get the job done. All right. Let's do an example. So it's the same instructions as last time. Does the integral converge or diverge? If it converges, we'll find the value. So with these, like I was saying, it's possibly a little bit harder to recognize why it's an improper integral. We have to think about, where is this function continuous? Of course, this one's not too hard. A common reason for a discontinuity, in fact, one of the most common reasons, is dividing by 0. So this is, it's discontinuous when x is 0, and that is the left endpoint of our interval. So I'm going to do the limit as t goes to 0, and I'm going to stay in between 0 and 1, so meaning I'm going to do the limit as t goes to 0 from the right, t to 1. This is exactly like this one. All right. So this antiderivative is just natural log absolute value of x. Go from t to 1. So I get, okay, natural log of 1 is 0. I plug in t. And now I have to think, what's the limit as t goes to 0 from the right of the natural log absolute value of t? Well, I guess these absolute values aren't doing anything because I'm going to 0 from the right. So I'm considering values of t that are close to 0 but strictly greater than 0. So these absolute values don't do anything. But more importantly, when I think about the graph of y equals ln x, here's my mental picture of it. This has a vertical asymptote when you approach x equals 0. So this limit is negative infinity. So, well, it has this negative sign in front too, so I guess we would say it's positive infinity. And in this case, we just say it diverges. Converges means that it has a finite value. So this one diverges. All right, moving along. All the examples today have the same instructions. So converge or diverge. If it converges, we'll say the value. So here we have x ln x. And so let's think again. Where is this discontinuous? Natural log has a slight issue. I can only do the natural log of a positive number. I can't even do the natural log of 0. It has to be strictly positive. So that's the problem. The problem is that I have 0 as my left endpoint. So that's the problem. So I replace the problem with t and do the limit as t goes to that. And again, this is the lower endpoint. I'm going to consider values of t that are in between 0 and 2. In other words, I'm going to go to 0 from the right. Okay, so that just happened. Now the next step would be to try to find this antiderivative. And the last one was easy, but this one we have some work to do. How do I find the antiderivative of x ln x? Well, luckily we learned techniques of integration. Let me go off to the side just to work on this. I'm going to forget about the limits of integration. I'm going to forget about the t going to 0 part and just work on this antiderivative, and then I'll come back to what I was doing. This looks like integration by parts. I see a log. So that's going to be u. X dx is going to be dv. du is 1 over x dx. V is this antiderivative, so 1/2 x squared. And this turns into, okay, u times v. Maybe I'll write the v first because that looks nicer. minus the integral of v du. Integral of v du. So I'm there. Let me clean this up a little bit. I've got a 1/2 that I can pull out, and then x squared, and a 1 over x that just turns into x. Okay. So this becomes a 1/2 x squared, and I've got this 1/2 as well, so I'll write 1/4 x squared. And I'm not going to bother writing plus c because this is just going to go here, and I have limits of integration. Going back to what I was doing, picking up from here, this turns into limit t goes to 0 from the right. We just found this antiderivative. So I'm copying this down. And then I do this from t to 2. All right. Now I've got an easy step where I just plug these numbers in. Okay. 1/2 of 4, so I've got a 2 ln 2 minus 1. And that's me plugging in 2 for x. And now here's me plugging in t for x. 1/2 t squared ln t minus 1/4 t squared. Okay, actually, let me do another easy step. Yeah, there's barely anything that's going to happen right now. I'm just getting rid of the parentheses. So these parentheses never did anything, and I'm going to distribute this negative sign. Okay, let's take inventory. I need to do the limit as t goes to 0 from the right of this. Now, part of it doesn't even have any t's, so this is going to be easy. This just goes to what it already is. This, well, let's think. T's going to 0, but I have to be careful. It's very tempting to say 0 times anything is 0, but actually, if I think about what this is undefined. Ln of 0 is undefined. As t goes to 0 from the right, actually, I can pull up the picture that we just drew last time. This is just the graph of y equals ln x. If you remember, as t goes to 0 from the right, this is like a vertical asymptote. So natural log of t as t goes to 0 from the right, that's like negative infinity. So unfortunately, as happy as I was to see that this goes to 0, I'm unhappy that this goes to negative infinity because this is a 0 times infinity form. So we're going to have a little bit of work to do there. But let's continue taking inventory. This is just 0. T is going to 0, 0 squared is 0. I'm not multiplying this by anything that could go to infinity, so 0 is just 0. So the only thing I need to work out is what happens with this guy. So let me forget about everything else. I'll even forget about this 1/2 for the time being. When I come back and put my final answer together, I'll have to remember that this 1/2 was there. But as long as I figure out what happens with the t squared ln t, I'll be in business. And as we discussed, this is a 0 times infinity form, so let's do the thing we do with those. I don't want to put 1 over ln(t) on the bottom, because I'm going to have to take the derivative of that if I do, and I don't want to do that. I'm going to leave the natural log t on top and put the t squared on the bottom, or in a manner of speaking, actually, it's the reciprocal of t squared on the bottom, right? Okay, now this is supposed to be something I can use L'Hopital's rule on. Let's check. Well, as we discussed, natural log of 0 from the right is going to infinity. As t goes to 0, this is like 0 to the minus 2, another like 1 over 0 squared, which is also like infinity. So this is an infinity over infinity form, so we are justified using L'Hopital's rule. So this is the limit, t goes to 0 from the right, of 1 over t divided by negative 2t to the negative 3 would be that derivative, right? So, all right, let's clean this up. Yeah. So I've got a negative 2 on the bottom. This is awkward, but I'll just do that with it. But I want to say t to the minus 3. That's like t to the minus 3 in the bottom is the same as multiplying by t cubed. So I cancel a t. I've got minus 1/2 t squared. And now this is an easy limit to do. T is going to 0, so this is just 0. Okay, let's remember what we were doing. We were doing this integral, and I worked it down to this point, and then we said, oh, we got a little thing to work out here, but we just figured out this goes to 0. So let's pick back up. So our original integral, the one we were originally asked to find, is, okay, nothing happens there, 2 ln 2 minus 1, and then I'm going to minus this, which is 0, and but yeah, like I said, we have to remember that 1/2 is there, but half of 0 is still 0, and then plus this, which we knew was 0 a while ago. So I get 2 ln 2 minus 1, which is finite. So this one converges, and the value is 2 ln 2 minus 1. Okay. So now let's just do some sort of random improper integrals. So I decided to, let's do another one of the first type, the one where it's obvious why this is an improper integral, because it has infinity there. So I'll just go directly to this. Infinity gets replaced with t, and I do the limit as t goes to infinity. Okay, so I'm like that, and now I have to somehow find this antiderivative. And this is not something that I have memorized or anything like that. So let me cordon off a little zone for me to work on that part. Oh, it got blurry. All right, that's better. Okay. So it's like this. I would suggest, because I see a composite function, I see a substitution. I'm going to let w be the inside of this composite function. Of course, that's the same as negative x to the negative 1. dw is then, so I bring the negative 1 down, so now it's positive x to the negative 2, right? dx. So this is the integral of, well, the top is just e to the w. And if I'm putting everything together right, dw is x to the minus 2, which is equivalent to an x squared on the bottom. So actually, if I just write my dw right there, that takes care of everything. Like, this takes care of my e to the minus 1 over x, and this is 1 over x squared dx. And so everything is there. Okay. And this is an easy antiderivative. That's just e to the w. And I'm not going to write plus c because we have limits of integration. So I'll just skip that. I do want to put my answer back in terms of x. So e to the negative 1 over x. All right. Let's go back to the big picture. So I have the limit, t goes to infinity. I just found this antiderivative, which is this. One to t. Okay. There's an easy step, which is just plugging in these numbers. So this is e to the negative 1 over t minus e to the negative, I guess, just 1. All right, so here we are. I need to do this limit as t goes to infinity. And so I've got two separate things. I can look at these separately. This one doesn't even involve t, so this is going to be no problem. This one, well, t is going to infinity, and I like that because that means that this is basically e to the 0, which is 1. So I don't have to do anything crazy here. I don't have to use L'Hopital's rule or worry about indeterminate forms or anything like that. Yeah, sorry, unfortunately I made a little smudge here. Let me fix it. That was a negative sign. Anyway, we're good. So if I want to write 1 minus 1 over e, that's fine. I would take either of these as an answer. Oh, and it converges because we got a finite answer. Okay, moving on. Here's another one. I do not see negative infinity or infinity, so I have something to think about. Why is this an improper integral? In fact, in real life, you might get something like this, and you might not even know whether it's an improper integral or not. So you have to think about whether this function is actually continuous everywhere. Of course, in this section, we should strongly suspect that everything we get is an improper integral because this is the section on improper integrals. It would be weird if I threw a regular one in the middle of these. Anyway, we should check for division by 0, especially because I see a fraction. And indeed, I notice that the bottom would be 0 if x was equal to 5, which is my upper end. So now we know. So I should do the integral, replace a 5 with a t, and do the limit as t goes to 5. And I'm going to stay inside my interval, meaning I'm going to go to 5 from the left. Oh, whoops. While I'm doing stuff, let me call this 5 minus x to the negative 1/3. Okay. Now, I can do this antiderivative in my head. This is one of those simple substitutions. I like, this is like letting w be 5 minus x. So let me show you. So this antiderivative is going to be, I'm going to do the antiderivative the way I would normally do it with the power. So I'm going to have, I increase the power by 1, so it's 2/3. I put the reciprocal in front, which is, luckily I saved that. Nice save. Like that. But then I have to do 1 over the coefficient of x. That's how these simple substitutions work. And again, this is I'm just skipping the work of a simple substitution where I let w be 5 minus x, and dw is minus dx, and basically this negative is because of that negative. But that's all that happened. From 0 to t, I'm going to plug these numbers in. So this is minus 3/2 times, okay, I've got 5 minus t to the 2/3 minus 5 to the 2/3. Okay, now t goes to 5 from the left, and I'm taking a look at this part. This looks like I would get 0 to the 2/3. 0 to a positive power is just 0. And 2/3 is indeed a positive power. 0 to a negative power is undefined, or if you're doing a limit, then it's probably going to be infinity or negative infinity. But 0 to a positive power is just 0. This is just what it is. This doesn't even involve t. So we're good. So I've got a negative 3/2 times 0 minus 5 to the 2/3. So let's just call that 3/2 times 5 to the 2/3. Oh, and it converges, because we just got a finite answer. Great. Now let's, yeah, okay. Let me skip to this one. All right. I don't see infinity or negative infinity, so I'm asking myself, why is this an improper integral, or even is it as an improper integral? We should check for division by 0. Let's try to factor the bottom to see where it's 0. X minus 2, x plus 1. So if x is either 2 or negative 1, then I'm dividing by 0. Now, negative 1 is not in my interval, so I'm not worried about that. Two is why this is an improper integral. So my function has a discontinuity at x equals 2, which is right in the middle. It's not the right endpoint or the left endpoint. So I break this up where the problem is. I go from 0 to 2. And then the rest of the way from 2 to 4. All right, now I'm going to do these separately. There's a number of ways this could go. If these both converge, then I would say the whole thing converges, and the answer is just going to be whatever value this one has plus whatever value that one has. If either one of them or both of them diverges, then we would say the whole thing diverges. So let's see what happens. Maybe I'll work on this one. Yeah, so let me, I don't know, I'll call this number 1 and I'll call this one number 2. So number 1, this one has a discontinuity at the upper end. So I'm going to call this the limit, where I'm putting a t instead of where the discontinuity is, and I would do the limit as t goes to the discontinuity, in this case from the left. And I'm like that. Okay, now I have to integrate this thing, and it is a little bit of a conundrum. Let me go off to the side like I often do. Just to work on this antiderivative, and I'll come back and put my answer in. All right, anything can pop up when you're doing these, and this reminds me of partial fractions. Okay, let's run through the steps. First, we should check whether we need to do long division. The degree on top, I don't see any x's on top, so I can act like the top is like x to the 0, so the top has degree 0. The bottom has degree 2, so I don't need to do long division. If the top has a smaller degree than the bottom, then I don't need to do long division. Step 2 is when I want to factor the bottom. Oops, yeah. Actually, I factored the bottom just a minute ago. Now I want to write the partial fraction decomposition. So let me write, so this is, like on top, this is like a 1, and on bottom, this is, I'll write the factored form. It's x minus 2, x plus 1. And what is the partial fraction decomposition? Well, this is a simple situation. I just have a linear factor there's no power on this, so it's like a 1. So I'm just going to have something with an x minus 2 on the bottom, and I'll stick a letter on top. I just go down the alphabet, so I start with an A, and then x plus 1 with a B. Now we find A and B. I'm going to multiply both sides by something to kill all the bottoms of the fractions. So that's x minus 2, x plus 1. Now, on the left-hand side, that just cancels the whole bottom and I just get 1. On the right-hand side, I have to be a little careful to distribute this separately here and also here. So when I distribute this here, the x minus 2 cancels and I'm left with the x plus 1. When I distribute this here, the x plus 1 cancels and I'm left with x minus 2. Now we plug in our convenient values of x. So let me make this disappear. I'm going to plug in x equals -1. That tells me 1 equals, okay, this is gone. This is -3b. So b is -1/3. All right, making progress. So I just made this disappear. Let me make this disappear. So I plug in x equals 2. I get 1 equals, this is going to be 3a. And then this disappears. So a is 1/3. Okay. So going back to what we were doing, we were trying to integrate this. We can now rewrite this because we said that it's a over x minus 2. So that's 1/3 over x minus 2. Plus b over x plus 1. So that's -1/3 over x plus 1. And now we can integrate it. 1/3 natural log absolute value x minus 2 minus 1/3 natural log absolute value x plus 1. And I'm not going to put a plus c because I have to remember what I'm doing. All right, that was a fun adventure. Let's go back to what we were doing. So limit as t goes to 2 from the left. I just found this antiderivative. It's this. I'll copy it down. Oops, yes, ooh. I almost don't have room for this. But right, I'm supposed to plug in 0 and t. Sorry about how that looks. All right. So I'm there, I put in t, so I have 1/3 ln t minus 2 minus 1/3 ln t plus 1 minus, this is getting a little big, so I'm going to do this on 2 lines here. I'm supposed to plug in 0. So this would be 1/3 ln 2 because there's an absolute value there. So yeah, minus 1/3 ln 1. Oh, ln 1 is just 0, but I'll take care of that in the next step. All right, so where does that leave us? So there's certain parts of this that don't bother me at all, like the parts that don't depend on t, they're fine. Like this is just whatever it is. This, like I said, is actually just 0 because natural log of 1 is 0. Now let's look at the things that do depend on t. There's this one, and I see myself about to think about natural log of 0 again, because if I put in 2 for t, I get natural log of 0. That is, do I have my picture anymore? Yeah, natural log of 0 is, I mean, natural log of something going to 0 from the right is negative infinity. So this goes to negative infinity. Let's keep going though, because it's possible that I would have like an indeterminate form. Like if I have an infinity minus infinity, then that's something that I'm going to have to think about harder. This isn't going to be any kind of infinity though. T is just 2, so this is like 1/3 ln 3. So what am I left with? I've got something going to negative infinity, and then something that's finite is 1/3 ln 3, and then I've got another thing that's finite. So basically I'm taking negative infinity and then I'm adding some finite numbers. This limit is negative infinity. So where does that leave us? Going back to what we were originally doing. We had this integral, we said, oh, this is discontinuous at x equals 2, so we break it into this one and this one, and all this time we've just been working on this one. And what did I say would happen? If both of these converged, then I would say the original one converges and its value is just whatever this is plus whatever this is. But that's not what happened. We only looked at this one, but we just figured out this one diverges. So after all of this work, I'm thankful that I don't even have to look at this one. It doesn't matter what this one does. By the way, this one also diverges, but it doesn't even matter. Even if this converged, the answer would be the same. If one of them or both of them diverges, then the whole thing diverges. All right, so we got it. All right, let's see here. I don't have that much time, so let me try to do this one. It's obvious why this is improper. I've got an infinity right there. So limit t goes to infinity, 0 to t, sine theta e to the cosine theta d theta. How am I going to integrate this? Probably substitution. I see a composite function. Let me go off to the side just to do that. W is cosine theta. dw is negative sine theta, which I like because I see that there. This turns into e to the w, and that takes care of the e to the cosine part. And if I just write negative dw, that takes care of the sine theta and the d theta, just because of this negative sign. Okay, looking good. So the antiderivative is just negative e to the w, and I'm not going to write plus c because of what I'm doing. Let me write this in terms of the original variable theta, negative e to the cosine theta. Okay. Going back to what I was doing. Yeah. Limit as t goes to infinity. I just found this antiderivative, it's negative e to the cosine theta, 0 to t. So what is that? I plug in t, and then I subtract negative e to the cosine 0. So that happens. And all right, I've got to do the limit as t goes to infinity, and so this part's fine. This doesn't even depend on t, but I have to think about this part. So now Of course, the graph of cosine this is as good of a picture as I need right now. There's no limit as x goes to infinity. It just keeps going up and down forever. So this limit as t goes to infinity of cosine t, that doesn't exist. It's not infinity or negative infinity. It's just a limit that doesn't exist. It just oscillates between -1 and 1 forever. So this limit does not exist, and so that means we would say it diverges. It only converges if it has a finite limit. We say it diverges if it's infinity. We also say it diverges in this case where the limit just doesn't even exist. All right, so we got it.